Well, hi there, boys and girls. Today we're going to go further into differential equations, and we're going to get more practice on separating variables, integrating both sides, handling an initial condition, and seeing if we can't come up with a y equals at the very end. So off we go. Here we're given a differential equation, and we're supposed to find the solution. That means we have to solve it for y equals, and we have an initial condition of 0, 1/2. I like to write it like this. I just, for some reason, like to see the x and the y written like that. So f of 0 equals 1/2 means the x is 0 and the y is 1/2. So of course we know the first step here is we want to separate variables. So I'm going to have e to the 2y dy is equal to 3x squared dx. So that's step one. Of course, on a free response question, this gives me 1 point. Yay! Now I have to integrate both sides. So I'm going to put an integral here, and I'm going to put an integral here. Now you should remember that the integral of e to the u du is e to the u plus c. But this du has to be here. The du stands for the derivative of u. For my example, my u is 2y. Now the derivative with respect to the derivative with respect to y of 2y is 2. So du dy is 2. I want to solve this for just dy, so I'm going to rewrite this as 1/2 du equals dy. So this integral over here turns into integral of e to the u times 1/2 du. And on the other side I have the integral of 3x squared dx. Okay, so the integral of e to the u du, of course, is just e to the u, so this is 1/2 e to the u, where u is 2y. A lot of you are to the point where you could just put a 2 here and a 1/2 out here to make the chain rule happy. But not everybody's there, so I went through the whole substitution. And on the other side, of course, the integral of 3x squared is x cubed, and then we put the plus c over there. And I did not give myself enough room here. What is wrong with me? Oh well. Alright, so at this point you can stop since you've integrated, and you can go ahead and plug in your x and your y, or you can go ahead and try and solve this for y equals and then plug in your x and y. It doesn't matter. I'm going to go ahead and plug in my x and my y. My y was 1/2 and my x was 0. So I will have 1/2 e to the 2 times 1/2 is e to the first equals 0 plus c, or c. So in this form right here, c is 1/2 e. So I now have the equation 1/2 e to the 2y equals x cubed plus 1/2 e. That's sort of a weird equation. And am I done? I'm not. I'm close. I have separated variables, I integrated both sides, I put my plus c, I handled my initial condition, but now the last thing I have to do is make it y equals. So the first thing I'm going to do is I'm going to double both sides. I'm going to multiply both sides by 2 to clear my fractions. So that gives me e to the 2y equals 2x cubed plus e. And then the last step is we have to solve it for y. Now you learned this in pre-cal. If your y, or your variable you're looking for, is up in the exponent, you're going to have to use logarithms. So I'm going to take the natural log of both sides. The natural log of e to the 2y equals the natural log of 2x cubed plus e. And then you should know that the natural log and e basically cancel, because this 2y can come down here in front, and natural log of e is just 1. So I get 2y equals the natural log of 2x cubed plus e. And then my last step is just to divide by 2. So dividing by 2, I get that y equals the natural log of 2x cubed plus e divided by 2. So that's my solution to that differential equation. Now part B is asking me to find the domain. This is something we haven't looked at before, but it's definitely a potential question. We need to know for what values of x can we use this solution. And we need to look here, and we need to remember that natural log is only defined for values. Natural log of x is defined only if x is greater than 0. So I need all of this after the natural log to be greater than 0. So I'm going to have 2x cubed plus e must be greater than 0. Keep in mind, if you cube a negative, you get a negative number. So let's solve this for x by subtracting e and then dividing by 2, and then we are going to take the cubed root. The cube root of both sides, and so we will get that x must be greater than the cube root of negative e over 2. That's sort of a weird domain, but I think that that is the correct answer for that. All right, let's see one more that's a little tricky. And here I've got a physical example with velocity of a skydiver. Something I'd like to do, but I think I'd be too scared if I actually got up. I don't know if I'd ever jump out of a plane. After her parachute opens, her velocity satisfies the differentiable equation dv dt equals negative 2v minus 32 with an initial condition. So first of all, we have to use separation of variables to find an expression for v in terms of t. That was like, this is similar to y equals f of x. They're asking you here to find some function of t. They want you to find v equals. So what we're going to do is take a look at what we have. We have dv dt equals negative 2v minus 32. Now this one is tricky because I cannot cross multiply to get my v over here with the dv because of this minus 32. So what I'm going to have to do before I cross multiply and separate my variables, I'm going to factor this side. So that's going to be dv dt equals, pull out a negative 2 and we get v plus 16. So now I get to where I can cross multiply basically, or I can divide both sides by v plus 16. So I'm going to get that dv over v plus 16 equals negative 2 dt. So that was a sort of a tricky question. I had to factor first so that I could, cross multiply basically. At this point we're going to integrate both sides, and I will get that the natural log of the absolute value of v plus 16 is equal to negative 2t plus c. This is a perfect natural log integral, and the integral of negative 2 dt is negative 2t plus c. Again, I did not give myself enough room. Okay, at this point, again, you can plug in your numbers if you want to, or you can go ahead and solve it. I'm going to solve this one first to show you that you can wait till later to find your c. So this has the natural log has a base of e, so I'm going to rewrite this. I'm going to scoot down here. I'm going to rewrite this as e to the negative 2t plus c power equals the absolute value of v plus 16. Now at this point I know that e to any power is always positive, so I don't need the absolute value. And again, I'm going to use this trick that e to the negative 2t plus c power can be rewritten as e to the negative 2t times e to the c. And again, e to the c is just a constant, so I'm going to rewrite this as c e to the negative 2t power. So I have that c e to the negative 2t power is equal to v plus 16, and I can just subtract 16 from both sides and I'll have my v equation, and this is a general solution. I hope I said subtract 16. I can't remember if I did or not, but whatever. Okay, so here we go. At this point I'm going to plug in my initial condition. My initial condition was 0, negative 50. So negative 50 for my v and 0 for my t. So negative 50 equals c times e to the 0 minus 16. Of course, e to the 0 is just 1, so I'm going to get that c equals negative 34, because adding 16 to both sides, and I finally have my answer. V equals negative 34 e to the negative 2t power minus 16. Now you could rewrite this as negative 34 over e to the 2t power minus 16 because of your properties of exponents. And I'm going to do that for my next question, because my next question, which is way back up here, Ask for the limit as t approaches infinity of v of t. That's called terminal velocity. How fast could you possibly go as time went to infinity if you never hit the ground? It's not the falling that's that hurts. It's that sudden stop at the end. So I want to find the limit as t goes to infinity of v of t. So what happens as t gets really, really large? If t gets really, really large, I'm going to have negative 34 over a huge number minus 16. Well, this effectively goes to 0. Negative 34 over a great big number is basically 0, and so I'm going to get negative 16, and that is going to be in, I think, feet per second. Okay, so that's a couple more examples of differential equations, and you guys are going to work on that tomorrow, and I will see you guys then.